This is Math 2414, Integral Calculus Exam 2 review. So let's go ahead and get started. Oh, well, I guess a brief topic overview. We're going to have arc length. We're going to have surface area. We're going to have differential equations. We're going to have parametric and polar calculus, and we're going to have sequences and the beginning of series. So we'll start with arc length formula. So not arc length function, this is formula. The function is in a couple slides. But this is a formula for the arc length when we have a specific curve. This curve has to be y as a function of x, which is like what we're used to so far. And it's given by this formula, the integral from a to b, the square root 1 plus derivative squared. So this is in this first one. This first one is in Newton notation. The prime notation, I think we can thank Isaac Newton for that. And this dy dx notation, this is the same formula. It's just the f prime is written as dy dx. And then I wrote a little note. We can hardly ever find the exact answer to these integrals because of the square root. We would have to integrate, this nasty square root of 1 plus something squared, and it's a very hard thing to do. So luckily we have the problems associated with arc length formula. They're usually rigged so that they end with, you can solve the integral with techniques we know from, I guess, the previous exam. Building on itself for sure. And, these integrals require the techniques of integration that we learned for the last exam to solve. And this is the same formula, just whenever, let me go back. So here we had y equals f of x, but now it's kind of flipped. This is x equals f of y, when x is a function of y, and then we have this formula. It looks the same. So this dy formula is when we have x equals a function of y. So and then we have the arc length function. So this function is defined as the definite integral from a to some value x. So x is like the variable that this function is in terms of, right? This s is a function of x, and then the x comes in as the upper bound for the integral. And so we call this t right here. There's a t dt. That doesn't really affect our answer in any way. We could have put any variable in there. So we call the t a dummy variable. So we could have put f prime of u squared du. And then off to the side here, I took the derivative of s. That's this function we just defined in terms of x. So I took ds dx. That's the derivative of this guy. And from the fundamental theorem of calculus, we have the derivative of an integral is, we just plug in the upper bound. And so I kind of manipulated, it's not very proper, but it serves as a mnemonic for remembering these formulae. You can remember this in symmetric form. ds squared equals dx squared plus dy squared, and then you either solve, for you either divide out by dx squared or dy squared, and you can actually arrive from this symmetric form at either one of these formulae. You can either have the y, the dy, or the dx from this symmetric form. And it's not proper to split up the derivative operator like that, or I guess the derivative function like that. But we do it at other times as well. We do it in separation of variables, which will be covered as a solving method for ordinary, or I guess also partial, but in this case ordinary differential equations. Yeah. So now we have surface of revolution. So there's like, from these two formulae, there's like 4 things that could happen. So like, first, we could have revolution about the x-axis, and in which case we would use this formula. But we may be revolving about the x-axis, and the function we are revolving is x equals a function of y, and that would affect the ds. We would use the same ds as so maybe I didn't explain that. ds is L. ds is like the arc length, what we're integrating in the arc length. So like it's this guy, this the square root of 1 plus dx dy squared. So that's what we call ds. And so ds could either be gotten from the derivative of x with respect to y, or y with respect to x. And in a similar manner, if we have revolution about the y-axis, we could either have x as a function of y or y as a function of x, in which case that would change ds. And so really from these two formulae, we have 4 possibilities of things that could happen. We could be revolving about the x-axis, and then our function is y is a function of x. And or we could have about the x-axis, and then we could have x as a function of y. And the same two options over here, when we revolve around the y-axis, exhaust all options. So there's 4 of them. So yeah, this is surface area of revolution. I didn't really go into where the 2 pi y thing comes from, but this surface area of revolution, we are taking tiny slices of arc length and converting that to like sort of like a cylinder, and then we're calculating the we calculate the what is it? The surface area of the cylinder. And so surface area of a cylinder would be circumference times height. And so you can see now the 2 pi y and the 2 pi x, that's simply circumference. And then ds is like the height that we're multiplying by. And then when we integrate, it's like adding up an infinite number of these surface areas of cylinders, really skinny cylinders. And so that's where we get the 2 pi y. Differential equations. We're going to have 3 topics on differential equations. Actually 4. Yeah, 4. So verifying a solution, that's just plugging it into the differential equation given. So like they'll tell you the answer and they just say show that this works out. So like you'll have some differential equation and then some function, y is a function of x, or whatever the independent variable is. And you simply take as many derivatives as you need and plug everything into the equation in the proper manner, and get out of it, you should get a true statement. If you plug something into a differential equation and you get a true statement out, then it's a solution and verified. Equilibrium solutions, that's where the differential equation is zero. So I guess these next two bullet points, I didn't put bullet points, but so equilibrium solutions and intervals of increase and decrease. I think these only really apply to first order differential equations, and that's really all we're going to talk about is only first order. So the order of the derivative is how many, the order of the differential equation is the order of the derivative that occur in the differential equation. So if we have like a fourth derivative, then that would be considered a fourth order differential equation. We're only dealing with first order, and we're only dealing with one type of first order. We're only dealing with separable differential equations, which the solving method for those only requires integration twice. You just have to integrate two things, and then you can solve it. So if your integration skills are good, then you can solve every separable differential equation like that. Just integrate twice. And then these intervals of increase and decrease, this is just where the derivative is greater than 0 or less than 0. And so for these last two bullet points, the equilibrium solution and interval of increase and decrease, you're going to want to solve for dy dx or dy dt or d whatever. They might change up the variables you're working with. But you would want to solve for the derivative. Get that on one side of the equation by itself, and then do the work. That will just make it easier. So here's separable differential equations. I talked about this a little bit. So if we have the derivative dy dx can be separated into this form where it's a function of x times a function of g, or a function of x times a function of y and multiplied by, then you divide on both sides of the equation by g of y, and you do the thing where you separate the derivative operator or whatever, and you separate it into the integral dy divided by g of y equals the integral f of x dx. And then after you perform this integration, hopefully you can solve for y. If not, you would have to leave it in implicit form. So if you cannot explicitly solve for y, then it's okay to leave it in implicit form. Now, one thing about this dy dx, so in a differential equation, the dependent variable is always on top, and the independent variable is always on the bottom of the dd operator. So it tells us a lot of information when we have dy dx. It tells us that the solution variable is y, and it tells us the independent variable is x. When a differential equation only has one independent variable, then we call it an ordinary differential equation. We will only be dealing with ordinary differential equations and a small subset of ordinary differential equations. So we're only taking derivatives with respect to x. Only one variable. I mean, it could be some other variable, but the point is we're only taking derivative in one variable. And then any differential equation will only have one solution variable, as far as I've seen. So that's about it for differential equations. We have parametric derivatives. So these are just some formulae you would want to know for the exam. So it turns out that the derivative dy dx, this is just y prime, it equals the ratio of the change, how y is changing with respect to time, divided by how x is changing with respect to time, provided dx dt is non-zero. If dx dt were 0, then we would be dividing by 0. And so it turns out when dy, or when dx dt is 0, that's actually a vertical tangent line, which is possible now with parametrics. So you think about functions of x, y is a function of x. It has to cross, or it has to pass the vertical line test to be even considered a function, right? When we draw a vertical line through any place on this graph, it can only cross it at most one times. That, however, is not the case with parametric equations. We can draw vertical lines and it can cross it many times and it still be considered a function. So long as the curve, no, I can't think of when it wouldn't be a function. Well, so long as you don't assign like 2 positions to one time value, which would be silly to do. You can't be in 2 places at once. So, so the point is, we don't have to worry about parametric equations. Free us up to do a lot more things. We don't have to worry about passing the vertical line test or whatever. So, and then as a result, we can now have like a vertical tangent line situation. Before, when it was just y as a function of x, that could never happen. Well, could it happen? No, I don't think it could. Maybe with like a unit circle, and you, but even then you would need a parameterization. So yeah, basically parameterizations free us up to do handle a lot more curves. And then here's the second derivative. So the second derivative, you take d dx, dy dx. Well, we already knew that, didn't we? d dx of dy dx, that is just the definition of second derivative. And then they expand it on the next guy. D dt. Oh, I just realized what I can do. Oh wait, I don't think I can point on here. If anyone knows how to point on Blackboard Collaborate, maybe Brian knows how to point on here. I want to have a little pointer on this screen. I don't know how to do that, but so yeah, it's just this formula. I mean, I just recommend remembering it, or if you're allowed to have a formula sheet. Oh, you can. Okay, thanks, Brian. So yeah, that's parametric derivatives. So like questions they could ask you on these parametric derivatives would be like questions, where is it increasing? Where is it decreasing? Where are the horizontal tangent lines? Where are the vertical tangent lines? All that information is encoded in the first derivative, dy dx. So it's increasing when dy dx is positive. It's decreasing when dy dx is negative. I don't think that's working. Maybe Control L or something? I don't know. Bottom 3 buttons. Oh, you're talking about Google Slides. Oh, sweet. Okay, you guys can see this thing? That's awesome. Okay, sweet. Okay, so yeah, so with respect to this equation, there's only 4 questions they could ask you. I guess 5 or 4. So increasing, decreasing. It's increasing when it's greater than 0. It's decreasing when it's less than 0. And if this equals 0, if this is exactly 0, then that would force the numerator to be 0. If the numerator were 0, that's just the y derivative with respect to t is 0. Then we have a horizontal tangent line. It's going sideways. Now, if dx dt is 0, now we have a vertical tangent line. Okay. And then with respect to this equation, d squared y dx squared, they could ask us about concavity. Where is it concave up? Where is it concave down? Where is the point of inflection? Okay. Parametric integration. I only gave one of the formulae for this, but there's two. So this is area. I didn't really write anything on this slide, but this is area, guys. So area of a parametric curve, and this is actually area between the x-axis and the curve because the dx. So we have a similar formula for area, but when it's like a function and we're trying to a parametric curve and we're trying to find the area between the y-axis, the other axis, and the curve. In which case we would change y. So write this on your paper next to this one. We have the integral like c to d x dy. You just swap the positions of these two. And then as a result, you would have like f of t g prime of t dt. So you can do either. There's two options for this formula. You can do this one right here is about the x-axis, and then the other one I was just talking about is about the y-axis. And then notice that the A changes to alpha and the B changes to beta. What gives? Why did those change? Why did the bounds change? Can anyone answer that question for me? And can someone describe how to get the bounds? Like how to determine what alpha and beta are? Okay.
Didn't they change because you changed the variable?
That's right. Yeah. So this first integral is dx, and then the second integral is dt. And so alpha can be gotten by determining which t value would produce an x value of a. Which t value would produce an x value of a, and beta is which t value would produce an x value of b. So it's actually solving for t. It's the opposite of plugging into the function, plugging t into the function. We say we would basically say f of t. We would say f of t equals a, solve for t. F of t equals a, and then solve for t, and then similarly for beta. Parametric integration, so we had area on the previous slide. The functions, that's a very good question. Yeah, I didn't ever declare that. So the function, the function, it's x equals f of t, and it's y equals g of t. Yeah, so that's how parametric um, curves are defined. Right? We have x as the function of the time variable, and y is a function of the time variable. Yeah, and then f prime, or yeah, f prime would be dx dt. Let me see. Let me see if I have anything else on this. Let me see if I can do this. No. Okay, so um, what was I gonna say? I was gonna say um, these parametric equations are a mapping between an interval, like an interval on the real line, to a curve in R2. So for every t value in this interval, we have associated with it exactly one x comma y pair. So it's really a mapping of the interval. So it's always going to be a line like that. When we have one parametric variable, then it will be a line or curve or whatever. And then here, it says it here actually. So I could have just showed you this slide. So x is f of t and y is g of t. T ranges from alpha to beta. It says f prime and g prime are continuous. They have to be continuous. So when a function has a continuous first derivative, we call it C1. If it has continuous second derivative, then it's C2. If it has continuous infinite derivatives, it's C infinity. So it's like a class of functions, continuous derivatives. And then we have this this equation right here. Now this looks awfully similar to, if we go back, this guy, ds squared dx squared plus dy squared. So it's the same thing basically. I mean, it is exactly the same thing. You could yeah, you could just remember this formula, and this formula would actually cover the other case that we had earlier. So like if I'm saying, like if the x was f of t, if x was only like the f of t was just t, then y would be like just a f g of t or whatever. So if we have x equals t, and then y would be g of t, which is also g of x. That would be the same as what we had earlier. And so we can parameterize graphs of functions like this. Set the x variable to be t, and then the y variable to be just whatever function we're looking at. So this is all for parametric integration, parametric calculus. Now we're going to talk about polar calculus, polar coordinates. So we start out with what we know. So r is a function of f of theta. This will be given. X, we know this from trigonometry. X equals r cosine theta. You could divide by r on both sides. You have x over r equals cosine theta. And then y over r equals sine theta. And so now in this next slide, or this next line, how do I get these lines, guys? Can someone tell me how I got these two? How did I get dx d theta and dy d theta? Can anyone tell me? Yeah. Plug in r into the equations and take the derivative. Yeah, and then we need the product rule to do it. So those are both correct answers. And so the minus sign comes from taking the derivative of cosine. The derivative of cosine is negative sine. And so the cool thing about this now is that we have basically parameterized x and y in terms of theta. So we have x and y in terms of theta. So it's a parametric equation. We can use this. So we're going to use this on the next slide. dy d theta over dx d theta. So the only thing that changed was instead of t, we have theta, which it doesn't really matter what we call it. And then we have the quotient right here. And then this is just what I got in these previous two lines. So if you don't want to remember this formula, you could get away with it. I only remembered x equals r cosine theta, y equals r sine theta, and then I would just do the product rule every time. I would just use the product rule every time to find this formula, and I wouldn't have to remember so much. So I had a calculus professor that strongly encouraged us to be minimalists in what we memorize. So I guess questions that could be asked on these polar derivatives would be like horizontal tangent lines, vertical tangent lines, stuff like that. Same questions we would ask about parametric derivatives. Polar area, so this is the formula right here. Area equals 1/2 alpha to beta r squared d theta. And so what happens, how do we get this? We have to remember that area of a sector of a circle can be found by 1/2 radius squared times theta. So sector of a circle, 1/2 times r times theta, and theta is the angle of how much of the sector we want. And so instead of like how we had this kind of same setup, but with Cartesian, the Cartesian is just x and y coordinates. So instead of having, in that case, in the Cartesian case, we approximated area with rectangles. Now we're approximating area with sectors of a circle. So that's going to change our integration formula just a little. And you can see how it changes. We have to square the function, and we have to multiply by 1/2. So subdivide the interval theta from alpha to beta. So alpha's right here, beta's up here. So subdivide this just like into a bunch of pizza slices, as many as you want. And then I guess they don't necessarily have to be of equal width, but it's just easier to deal with when they're equal width. Theta sub I plus 1 minus theta sub I. So I guess I ranges from 0 to n. And then we choose a test point in one of these intervals. We can see it in green right here. And we'll use this as the approximate radius, the angle at which the approximate radius occurs. And we can make these so thin that this approximate radius will actually be like the true radius. So the area of the ith slice, that's this pizza slice right here, can be approximated by area of a sector of a circle. And that's the formula I gave you. That's area equals 1/2 times radius squared times theta. And so how do we get from this delta a sub I to this integral? Well, we take a sum of all these I ranging from 0 to n, and then we take the limit as n goes to infinity. And that's how we define an integral, the limit as n goes to infinity of the Riemann sum. And then we have polar arc length. Just another formula. These aren't so bad because you'll have like sine and cosine in them, and things will like square and turn to 1. So these are not too bad. Okay, now we get into sequences. You won't have a question like this on your exam, but this is the definition of when a sequence has a limit. And I guess at this point, it's probably just better to like intuitively understand what's going on. So pick an epsilon, pick your favorite number to be epsilon. Epsilon is usually a very small positive number in math. And so we'll say, you know, let epsilon greater than 0 be given. And that represents a tiny little small positive number. So if we pick an epsilon, then there is an n, an integer, such that if n is greater than n, so all that's saying is everything after big N. All the terms in the sequence after this chosen integer. And this chosen integer will be in terms of epsilon. So like the corresponding integer, n is a function of epsilon most of the time. And so what this is saying is, as if we pick sufficiently large n, then the distance, right, absolute value is just a distance. So the distance between an and L is less than epsilon. And since epsilon was chosen to be arbitrarily small, it's to say that we can get as close as we wish to this limit value with the terms of our sequence. We can get however close we want with large enough n. This is important, this theorem. I didn't prove this, but I don't think it would be too hard to prove. You would have to use the definition on the previous slide. But what this is saying is we have a limit of a function equals L, and we have f of an integer is our sequence, a sub n. So a sub n and f agree on the integers or naturals. In this case, the limit of the sequence will agree with the limit of the function. So we can use like functions to represent these sequences and then take the limit of the function. Can anyone tell me, I'll let you know, I'm looking for a very specific answer. Can anyone tell me why it would be beneficial to look at a continuous differentiable function rather than a sequence? Can anyone tell me why it would be better in some cases to look at a continuous function rather than a sequence of numbers? A continuous differentiable function. I'm looking for something very specific. So I don't think we have a notion for continuity of sequences. We don't have a notion for continuity of sequences because it's like discrete points. Like we have to pick up our pencil to draw the next dot. So a sequence cannot be continuous. Anyone else? Good try though. I appreciate the engagement. Does anyone else have a guess why we might want to deal with a differentiable function rather than a sequence? And then this answer Jennifer provided, possibly will give you a hint. Like these sequences, they can't be continuous, they can't be differentiable. But if we have a differentiable function, Yes, you have a question. If let me finish this real quick. You can just type it in the chat. But let me finish this one thought. So if we have a differentiable function that represents our sequence, then we can use L'Hopital's rule. You can't use L'Hopital's rule on like a sequence or whatever because it's not differentiable. What's your question? Okay. The same limit laws hold. So if you remember the limit laws, this was from Math 2413, differential calculus. Limit laws are the laws that limits obey. Things like the limit of the sum is the sum of the limits. The limit of the difference is the difference of the limits. The limit of the product is the product of the limits. The limit of the, and so on. Just all the kind of like intuitive things that help us evaluate these limits. So it should be it's exactly the same as the limit laws for functions. So the vertical tangents of a vertical tangents occur. Dy dt is 0. Okay, that sounds good. So I'll keep on lecturing. Squeeze theorem still holds. That's actually not too hard to prove either. The squeeze theorem. So yeah, we still have the same limit laws, and we have the squeeze theorem still operating. Here's a theorem. Here's a theorem about sequences. So we have if the limit of the absolute value equals 0, then the limit of the sequence is 0. And I gave a counterexample initially, like something where the hypothesis doesn't hold. So like if we take this sequence right here, an, I forgot to write, but I should have wrote over here that the limit of the absolute value of an equals 1, because we just have the absolute value of -1 to the n, and that is always positive. That just turns to 1. So we have like the limit of the absolute value equaling 1. But then we can see that if we if we partition the natural numbers into even and odd numbers, then we get two different answers. We have two subsequences converging to different limits. And in that case, we would say the limit of the sequence does not exist because it's going in like two different directions. So this is an example of something where the hypothesis didn't hold, so obviously we don't get the conclusion. Okay. And then here's a graph of what -1 to the n looks like. So it's just either +1 or -1. It's +1 for even numbers, and it's -1 for odd numbers. So this is what this sequence looks like. And we can see now this is not differentiable. This is not continuous. Okay. And now this is an extension of, or like an example on this theorem. So now this is something where the limit of the absolute value of the sequence is 0. So then the limit of the sequence itself is 0. We have this guy, -1 to the n divided by n. So I provided a proof. So you will not be required to do anything like this right now for probably any of your math. But so like all this is saying is if we start with some positive number epsilon, and then we choose n to be this function of epsilon, Can anyone tell me what those braces, those half braces mean? Does anyone know what those braces mean right here? Yeah, it means round up. It's the ceiling function. So if we choose n to be this number, which is greater than 0, then and it's a natural number, because if we round up, then it would have to be natural. Then for any little n bigger than big N, we have this inequality chain holding. And this inequality chain is saying right here, a sub n minus L, our limit value. So a sub n minus L, well, the negative 1 to the n, that goes away from absolute value. And then the 0, well, we're subtracting 0, so that doesn't do anything. And so by the assumption that n is greater than n, we have that 1 over n is less than 1 over big N, which is less than or equal to, well, big N is just 1 over epsilon. So we have 1 over epsilon, which equals epsilon. And that's the end of the proof at that point, because we showed that the difference for a sufficiently large n, we showed that the difference of the sequence and the limit value, it can be made as small as we wish. So then this sequence is convergent. But we could have just used the theorem, right? We could have just said, oh, well, the absolute value of this guy equals 0. Therefore, the limit of this guy, the limit of the sequence with no absolute value is 0. So you could either use this nasty epsilon n proof, or you could just apply this theorem initially. You could say the limit of the absolute value is 0, so the limit is 0. And then here's the picture. Here's what's going on. Yeah. I actually don't know if I should call this sequential criterion for continuity. I'm not sure if that's the same. This might be slightly different, but I had a feeling that it was, so I went ahead and put it. Anyways, so we have this theorem. If the limit of a sequence equals L and a function is continuous at that limit value, then it's like the limit passes through the function. The limit passes through the function, and then we can just look at the limit a n as n goes to infinity. That equals L, so this is f of L. And then I gave a proof. So this is what we want to show. This is like the punchline. This is what we want to show. Now, if you remember, so f is continuous, right? F is continuous, so we have this statement down here holding. This is what it means for f to be continuous. If f is continuous, that just means there exists a delta greater than 0, so that all this business holds, right, for this epsilon. I'm actually looking at the time, and I think I just may skip over this, but I mean, if you're curious about this stuff, it is in Stewart's calculus book. You can just look at the proof for this. And here's an exercise for you. Determine the values of R for which the sequence R to the n is convergent. So try this on your own. We have monotone sequences. So a monotone sequence is either non-decreasing or non-increasing. So with this definition, constant functions are monotone. If you said a sequence is increasing and decreasing or whatever, that would kind of miss a case. That would miss if we had like constant function. So a sequence that is either increased I'm going to say non-decreasing or non-increasing. If it never like if it always exhibits one behavior, if it's always right here, guys, this should be less than or equal to. This should be less than or equal to. But yeah, so if we have a sequence that either is always going up or always going down, then it's monotone. Boundedness. If it's bounded above, there is some number m for which every term of the sequence is less than that number. You can just find it, just say, oh, well, every term is less than 2 or whatever. Same thing for lower bound, bounded below. If every term in the sequence is greater than some little m, then it's bounded below. A sequence that is both bounded above and below is considered bounded. The completeness axiom. This is special for the real numbers. Every non-empty subset A of R that is bounded above has a least upper bound. So this is very special. And we're going to need this for the proof of this monotone sequence theorem. Every bounded monotonic sequence is convergent. So instead of like evaluating a limit, we can just show that a sequence is bounded above and also show that it's either increasing or decreasing or non-decreasing or non-increasing, in which case we know it's convergent. We may not know what it converges to, but convergent. And then so here's the proof. And a couple of notes off to the side. So in this theorem, it says every bounded monotone sequence is convergent. So we can reformulate this to say if AN is bounded and monotonic, if we have these two conditions occurring, then we have the sequence is convergent. And so I provide this proof. This proof is in Stewart's calculus book. This is chapter 11.1. It's at the end of it. And I give you some, least upper bound is called supremum. That just means like it's an upper bound and it's the lowest of all the upper bounds. And so I won't go into this proof too much. But it's a nice theorem. We're going to need it for some of the problems that we'll do. Series. An infinite series is convergent if the sequence of partial sums is convergent as a sequence. So we have like the summation, like I or k, n goes from 1 to infinity. These are infinite series, right? So n goes from 1 to infinity, the sum of an. So then if we can write a formula, S sub n, where S sub n is the sequence of partial sums, then we would just take the limit of that sequence, and then the limit of that sequence would be the answer to the series. But unfortunately, we can't find this formula for the sequence of partial sums all too often. We can find it in the geometric case, and we can find it in the telescoping case. But we're not going to talk about telescoping series. That seems to be omitted from the exam, but that is an example that in geometric is an example of something that we can find formula for. We can write a formula for. And then when we write a formula for the sequence of partial sums, then it's simply take a limit. So this is a partial sum of geometric series. So this is if n is finite. If you want to consider when n is infinite, you need to take the limit of this. So S sub n right here is a limit, or is a sequence of partial sums. So if you take the limit of this, then this would be the limit value of the series, what the series converges to. And we get that exactly that right here. So if you take this guy, and as n goes to infinity, well, this guy will go to 0. Why? I didn't really say what the domain of R is, but R is between 0 and 1. So if R is in between 0 and 1, and we're taking the limit as n goes to infinity, this term will vanish. Then we'll have a times 1 divided by 1 minus R. So that's just a divided by 1 minus R, which is what we have right here. So a, I always remember a as, it's just the first term of the sequence. So maybe that'll help. And if R is bigger than 1 or equal to 1, then the geometric series diverges. A series that does not converge is said to diverge. This is the first test that we'll have for series. So not all the time we can find the number that the series converges to, but we can tell you if it's going to converge or diverge. We don't know what it's going to converge to or whatever, but we can tell you if it's going to converge or diverge. This test, however, only tells us divergence. It just tells us it doesn't converge. It doesn't tell us a whole lot. It doesn't. So we can like rule things out with this one basically. So if this is convergent, then the limit of the sequence has to be 0. Because if the limit of the sequence were not 0, then we would be adding up after like a sufficiently large n. After a sufficiently large n, we would be adding up like the limit value or things very close to the limit value. And so we would have like after the nth term, we have like say the limit value is 2, we would have 2 plus 2 plus 2 plus 2 forever. So obviously that will diverge. So it is a necessary condition that the limit of the sequence is 0 for the series to be convergent. However, that does not mean that if the limit of this sequence is 0, then it's convergent. So that would be, I guess, the inverse. The inverse does not hold in general. So, and then the contrapositive down here, if you know any logic, it's P implies Q is up here. This is not Q implies not P. And then this is not the complete sources, but this is I got a theorem from the completeness axiom from this one. My other sources are Stewart's calculus book and Desmos graphing online. So that is all I have for the PowerPoint. We're gonna take a small break and do practice problems in breakout groups. Okay. So we're gonna take a small break now.
So I'm guessing the head leader had some difficulties, so we're going to, I guess I'll be leading, just the one room. Okay, so I told my previous group that I'd be using an extra set of problems, and that would be, let me see. So there are Luke's problems, and there are also these problems. I'm starting off with these ones because they're a little bit easier for now, and then we can jump into them if you want. But let me go ahead and set it in the chat. So you guys can kind of browse that and see what the topics are, and they both have the questions and the solutions. So that's what I think is useful. Because if you don't have the answer key, it'd be good to kind of check the step-by-step process. Yeah. Okay. So my previous group asked for polar equations and polar area solving this type of questions, and then series and sequences. If you guys have anything you also want to ask in practice questions, go ahead and send in the chat, and we'll get to it whenever we can. Okay, so but we're starting with find the area that's inside these two equations. So essentially, it's a polar area kind of a question. So I'm going to, I think someone said that you guys generally have the kind of picture already in your problem. So I'll go ahead and get a Desmos graph for that. Let's see. Okay, so let me just go ahead and screenshot that into the Word document. All right. So this is the graph we're looking at. I believe the blue one is this one, and this is 4 or minus 2 cosine. And you can also kind of see that these graphs, if you need to, they're basically just big circles. If you know the equations and what the format is, you should be able to kind of see or graph the circles yourself. But this is what they look like from Desmos, right? And you want to find first the area that's inside the circle, right? So we know that the area inside the circle would be inside here, right? Let's see. And outside of this one. Oh, okay, so not that one. Let's see. So it's inside here. So this is one part of the domain. And then you also have outside of this big blue circle, right? So this is the area we're going to take, right? And so the hardest thing of doing these kind of problems is that you need to figure out where the bounds are and what to subtract and what to subtract from each other, right? So we also know that the area of a polar curve is 1/2 times the integral from, I guess, it's theta 1 and theta 2. And we know that we have this big circle, right? So we know that these coordinates are mostly likely going to be where they intersect, right? What angles did they intersect at? And that's most easily found by letting them equal to each other, these two r's, right? And then finding which angle that they intersect at. So that would be 4 minus 2 cosine theta is equal to 6 plus 2 cosine theta. And so we can do a bunch of math, right? Move the 2 cosine thetas over. Right, and then you're going to get this one over. I think it should be, let's see, 6, that's minus 2, equal to 4 cosine theta, and then 5 by 4, 5 by 4. You're going to get cosine theta is equal to -1/2. And so you want to find what angles was my cosine equal to -1/2. So on your circle, you know that would be at, let's see, I believe the angle is pi over 2. Or sorry, this is 2 pi over 3. And it's also at 4 pi over 3. Right, so this is our angles, and you'll see here that these are the kind of the angles that we see on these circles, right? So that is one of them done, right? We found where they intersect and we found the bounds. Now we need to find which one or what areas do we need to subtract from each other in order to get this area only, right? So let me see if I can use a different color. Let's see. So if we use purple, right? The area from, let me just mark these down, right? 2 pi over 3 to 4 pi over 3 for the blue circle would be this purple shade, right? Kind of makes sense, right? So this is that one. And if we have oh sorry, it's the purple shade is one for the red circle, right? That's the area for the red circle. If you subtract Let's see if I can get a good color. No, that's probably not. And then the yellow would be the area from the big blue circle, right? So if we subtract the whole purple from the yellow, you're going to get this kind of area on the outside, if that makes sense. I don't know if the colors kind of match, but hopefully that kind of makes sense. So we know we must subtract this red circle's area, which is r equals 4 minus 2 cosine theta, and we'll subtract it from this circle, or this part of the blue circle, and that's going to get us the outside area. So that's going to be equal to the blue one, which is 6 plus 2 cosine. All right, so we can set up our integral, and this is the area formula, by the way, with these two bounds and the corresponding kind of radiuses, right? So we can do 1/2 times the integral from 2 pi over 3 to 4 pi over 3. And that's going to be this area, right? That's the whole thing, subtracted by the small one. And that's going to be this outside area, right? So that's going to be 4 minus 2 cosine theta. That's the whole area, minus the inside area. So minus 6 minus 2 cosine theta. And then you're going to square, or let's see, actually, I think, okay, no, hold on. You need to square them individually, I believe. Sorry. Yeah. Oh, I think Luke found the stylus. Should we go back after, or right now, or should we finish the question? Let's see. I'll wait for a decision, but I'll continue for now. Okay. Right, so hopefully this makes sense, right? We have that big radius minus this small radius, right? Squared. And then if you solve this integral, this is the setup for just this area, right? Okay, so once we kind of set this up, essentially all we need to do is integrate, right? So I don't know if you guys want to continue with this integral, but I'll go ahead and kind of do it a little bit fast, and stop me if you guys have any questions. But essentially you're having this separate integral and this separate integral. And you can combine it if you want, it doesn't matter. So you have 16, right, minus the 16 cosine theta, and it would be plus 4 cosine squared theta, right? And that would be minus this square would be 36. And I guess I'll do parentheses for now. And then you have plus 24 cosine theta, and then plus 4 cosine squared theta, right? Theta. And in this case, oh, the bounds? Yeah, sure. Okay, so the bounds, right? We know that this is our picture, right? We know that r equals 6 plus 2 cosine theta is our big blue circle, right? And we have r equals 4 minus 2 cosine theta is this red circle. So in this case, in order to find where they intersect, right, we need to make sure that the r's are equal to each other. So we set the radius would be equal to each other at some angle, right? So we let this r function equal to the other one. That means that they'll intersect at the same radius, right? And then we solve for theta. So we got to cosine theta is equal to -1/2. We know that there's two angles that make cosine theta equal to -1/2, and that's 2 pi over 3 and 4 pi over 3. Yeah, and if you have trouble doing this kind of one, you can also just do arctan or cosine, right? If you prefer to do that. It should be the same thing, but Maybe some people prefer this notation. But once you get those bounds, then you kind of got to figure out what the individual areas kind of give you, right? So this circle will give you this big area. I don't know if you see my cursor. And then you have to subtract it with this area of the blue circle, and that gives you this outside area, right? And for this integral, once you get up to here, you can kind of simplify. I'll do real quick 36, right? Put all like terms together. Minus 16 cosine theta, which is minus 24 cosine theta. And then you have, these actually cancel out. So I think that's nice, right? Cancel out. Yeah, so those ones cancel out. And so you just integrate this one, which should be easy for y'all, and then you input the bounds, and then you should get your area. Just as a note, generally with polar areas, you are going to find integrals like cosine squared theta, right? Or things that have this thing in it. The kind of trick to solving those are essentially what's called a power reducing formula, I believe. And that's just a trig identity you guys probably have used already and probably kind of familiar with. But essentially, let's get rid of these integral signs. We don't need them. You break down cosine squared theta into 1 plus cosine 2 theta, right? You reduce the power over 2. And this one becomes the same thing, just but with a negative. And you'll see that these two are basically really easy to integrate, right? The only thing you need to worry about is maybe u sub, but as always, that any cosine or sine of something inside, if you integrate, that's just going to be negative 1 over a, or sorry, not negative because it's cosine, 1 over a times cosine of theta, right? So anytime you have a constant, you're going to divide by it and then do the normal cosine, keep whatever. Will this be a negative area? Oh, let me see. Did I miss it somewhere? Let's see. I think this one is this one. We're checking this one. You make a good point. 4 minus 2 theta. I don't think I got the wrong graph. It depends on what the values you get for 4 pi over 3 and 2 pi over 3. Because as you remember, those. Oh, that's true. Let me see. Because they should be. Cosine can have negative values, and so can sine. So I think the negatives won't matter until the end. I'll have to double check on that. Let's see. And this one is from the website, so let me just check the answer key and make sure I did it right. Just a second. I think it does turn out to be a positive answer in this case. Yeah, okay. And just so you guys know what I'm talking about. Let's see if I can change the picture. I believe you should end up with even with negative answers, right? So they get this one, they set it up properly like us, and they also get negative answers, but if you plug them in, you get a positive answer due to the nature kind of things, because this one will become something 0. So I wouldn't always look for if it's negative and try to think that it's not the right answer. It should be, as long as the final answer is not negative, it won't give you an actual error.
X equals y to the 4th over 8 plus 1 over 4 y squared. Y in this interval. So we need to do integral 1 to 2 ds, where ds equals the square root 1 plus dx dy squared dy. So we're going to calculate this inner part first. And series and you want series and sequences? You guys want this question? Yeah, we'll finish it. We'll finish it, and then I'll skip to the sequences and series. So dx dt, or dx dy, excuse me, is y cubed over 2 minus 1 half y to the third. We're going to square it. So I'll just call it x prime squared. X prime squared will be y to the 6th over 4. And then we have to do twice the product. So twice the product of these two. So that's 2 times y cubed over 2 times negative 1 over 2 y cubed. Well, the y cubes cancel. These 2's cancel. So this is negative 1 half for the inner term. And then we just square the last term to get the last term. 1 over 4y to the 6th. And so this is dx dy squared. So then we just need to add 1 to this. So 1 plus x prime squared is going to be, well, we have a negative 1 half. So we just add 1 to negative 1 half. This is positive 1 half. And then the magic happens right here. This actually factors into y cubed over 2 plus 1 over 2 y cubed. You can check this. You can FOIL this out. This is squared. And the cool thing about this now is we're taking the square root of the square, and so we can do the integral. So we're doing 1 to 2, the square root of y cubed over 2 plus 1 over 2 y cubed dy. And this is squared. The square root and the square cancel. And so this is the integral from 1 to 2, y to the third over 2 plus 1 over 2 y to the third dy. And then you guys can solve this integral, I hope. This is just power rule integration. This is direct integration, so I'll leave that for y'all. Yes, series and sequences will be on the test. So I'm going to go ahead and skip to, and then I'll come back if I have time. Yeah. What's up? Okay. So determine the limit. So if we have a(n) equals the natural log of n plus 1 minus the natural log of n, and we want the limit as n goes to infinity of a(n). This is the limit n goes to infinity of ln n plus 1 minus ln of n. And then this is equal to the limit as n goes to infinity of ln n plus 1 over n. And then we can apply that theorem. We had a theorem that said if f is continuous at L and the limit as n goes to infinity of a(n) equals L, then the limit as n goes to infinity of f of a(n) equals f of L. So basically the limit passes through. So we have ln, the limit n goes to infinity, n plus 1 over n. So n plus 1 over n, that's just 1. So this is ln of 1. So this is 0. So this sequence converges to 0. And then B. If we have an equals n cubed over n cubed plus 1, then the limit as n goes to infinity of an is equal to, I guess I'll work this out like how we did in Calculus 1, where we have a special one that we multiply by. And we're going to multiply by 1 over n cubed, 1 over n cubed. So this is equal to the limit n goes to infinity of 1 over 1 plus 1 over n cubed. Well, the limit as n goes to infinity of 1 over n cubed is just 0. So this is 1 over 1 plus 0 is just 1. Okay. C. an is 3 to the n plus 2 over 5 to the n. So this is actually just 9 times 3 over 5 to the n using exponent properties. And the limit as n goes to infinity, 9 times the limit, right? The 9 can pass outside the limit because it has no n. And so this limit, this is 0. And then this is sort of like the exercise for you. It's like determine the value of r for which this is convergent, this sequence is convergent, and it's only when the absolute value of r is less than 1. Okay? So like sort of like the geometric series type vibes with this, isn't it? Okay, so then D. For D, we have an equals n sine of 1 over n. Does anyone have a suggestion as to how to handle this question? How do we find the end behavior? How do we find the limit of an in this case? Does anyone know how to find this limit? You know what? I didn't think about that, but I think that will work. Let's do that. So sine of 1 over n. Wait, no, that doesn't work. I'll show you why. So let's try it. So we know this. This is always true. Yeah, it's L'Hopital. It's actually L'Hopital. I'll show you why this doesn't work, and then we'll do L'Hopital. So then I multiply this by n, like squeeze theorem requires. And then now we have our target in the middle, squeezed between, well, if we take the limit, this is negative infinity. So this doesn't really tell us anything. This tells us the limits in between negative infinity and positive infinity. So inconclusive, yeah, we need L'Hopital's rule. Before we do that, we have to let f of x equals x sine of 1 over x. Notice that f of n equals a n for all n in n. This means for all natural n. So this just means it agrees on the natural numbers. This function is the same as the sequence on the natural numbers. So we're going to do the limit as x goes to infinity of x sine 1 over x. These will have the same behavior. And then we notice that this is infinity times 0. This is indeterminate. This is indeterminate form. But it's not the correct indeterminate form to use L'Hopital's rule. Remember, to use L'Hopital's rule, It has to be either 0 over 0 or infinity over infinity. So we're going to rewrite this in a special way. We're going to rewrite this as the limit x goes to infinity. So we're going to keep sign in the numerator, but we're going to change this to have a denominator of 1 over x. You can check that these are equal by multiplying by the reciprocal. And now this limit is actually 0 over 0, which is good because it's the type of indeterminate we can handle with L'Hopital's rule. So by L'Hopital's rule, we take the derivative of the numerator. So this is going to be cosine 1 over x. We need the chain rule, negative 1 over x squared, divided by, and then the derivative of the denominator is just negative 1 over x squared. So these cancel. So this is just limit x goes to infinity, cosine 1 over x. And then this is cosine of 0, which is 1. So this limit, this sequence converges to 1. Okay. I'll skip this one for now, and I'll go to the series. So I have five series for y'all, and there's only 2 types of series on this exam. The next exam will have more, but the 2 types are geometric, and then we have divergent. So for geometric, we'll use A over 1 over R, and for divergence, we'll use the test for divergence. If you don't know what the test for divergence is, then good luck, but also just Google it. It was in the slides, but it's the only test in this exam. It's very useful for, well, testing for divergence. It doesn't tell us anything about convergence. So let's start. We have problem A. It just says determine if the series is convergent. If it is convergent, find its sum. So we have the summation n equals 1 to infinity, 1 plus 3, 2. So this is equal to the summation n going from 1 to infinity, 1 over 2 to the n plus 3 to the n over 2. Now, I'm forgetting my rules. Well, I know this is divergent. Oh, we have to use a comparison test, don't we? Yeah, we have to compare this to something. Because, like, I'm pretty sure you cannot just distribute this through. Okay, you can't distribute this through. You can only do that if under certain circumstances, and maybe Les can chime in if he knows. Yeah, someone said it in the chat. Don't we use a comparison test? Yeah, that is right. Yeah. We didn't learn. Oh, you didn't learn how to do a comparison test with these. Well, it's the same. It's the same as the integral comparison test. And then we know a series is geometric whenever it has like the n in the exponent. So a geometric series, it was on the slides actually. A geometric series will have the form a r n minus 1 or something like this. So this is how you know it's geometric. So I'm going to say 1 plus 3 to the n over 2 to the n. This is less than 3 to the n over 2 to the n. This is easier to handle. And then this series, we know, diverges. This is a divergent geometric. This is divergent geometric because r is equal to 3 over 2, which is greater than 1. So, actually, does that work? No, that doesn't work for my comparison. Oh, man. So, Yeah, I'm having trouble reasoning why this is divergent. But I guess what you could do, yeah, here's what you would do. You would use the test for divergence. So you just do the limit, n goes to infinity, 1 over 1 plus 3 to the n, 2 to the n. And then this is infinity over infinity. But I guess we could use like L'Hopital's if we think of a function. Or we could just split this up. Scratch this. We could split this up. Limit n goes to infinity, 1 over 2n plus 3 over 2 to the n. And then this is 0 plus infinity is infinity. So by the test for divergence, by divergence test, and I'll say like since the limit as a or as n goes to infinity of an is non-zero, then the sum n ranges from 1 to infinity of an diverges. Okay? Does that logic make sense? We showed that the limit of this sequence is non-zero, and so the series diverges. Sorry about that trip up, y'all. Yeah. Does anyone have any questions over this one? Well, this was geometric, and we used the divergence test. So if it's not, yeah, that's true though. What you said is right. If it's not geometric, then I would recommend using the test for divergence, because that's the only tools we have at this point. So we have, for this next one, something that looks almost identical. So we're just going to flip the 2 and the 3. So where the 2, this one was, so this is 1 over 3 to the n plus 2/3 to the n. And then yeah, I'm not sure, but I think since like if we call this an and we call this bn, and we notice that both an and bn converge by themselves, then so will their sum. This will also converge. I'm pretty sure this is right, because we couldn't get like infinity out of a finite number. So, but as opposed with the other one, was different because one of them was divergent. So this is equal to the sum 1 over 3 to the n plus the sum 2 over 3 to the n. So now we use our formula. So this will be 1/3 over 1 minus 1/3 plus 2/3 over 1 minus 2/3. So this is 1/3 times 3 over 2 plus 2/3 times 3 over 1. So this is 1/2 plus 2. This is 5 over 2. Okay. Okay. So next problem. Okay, this one's nice. So we have the summation n ranging from 1 to infinity, nth root of 2. So this is like saying we have like 2 to the 1 over 1 plus 2 to the 1 over 2 plus 2 to the 1 over 3. Does this converge or diverge? Well, we're going to find out. So an equals 2 to the 1 over n. The limit as n goes to infinity of an equals the limit as n goes to infinity of 2 to the 1 over n. And then we say f of x equals 2 to the x is continuous at x is equal to 0. And the limit as n goes to infinity of 1 over n is 0. So by that theorem, I think it was theorem 3 or something in PowerPoint, this is equal to, the limit passes through. The limit passes through the function. So this is 2 limit n goes to infinity 1 over n. So this is 2 to the 0, which is 1. 1 does not equal 0. So the sum an diverges by the test for divergence. So we just showed the limit of the sequence is non-zero, so that means the series diverges. Okay. Here's an easy one. If you know your trigonometry, arctangent of n. So we'll just do the limit as n goes to infinity of arctangent of n. And we know this is pi over 2, which is non-zero. So by test for divergence, the sum n equals 1 to infinity of arctan of n diverges. Okay. And then this one's pretty interesting. We have the sum n ranges from 1 to infinity, n squared over e to the negative n. So does anyone, oh wait, e to the positive, no, I got this flipped. Not this one, I'm sorry guys. We have e to the n over n squared. Tell me, what is your hunch? Do you think this one will converge or diverge? Does anyone have a hunch? Does anyone have a notion of what might happen? So So e is this is a very, very quick increasing function. This one is also increasing, but it's increasing slower. So it's like saying like we have a ratio of something that's growing divided by something that's growing. So like maybe not at first you can't determine what's going to happen, but if we say f of x equals e to the x over x squared, and then we do the limit as x goes to infinity of e to the x over x squared, we get infinity over infinity. So we can use L'Hopital's rule. So this is the limit x goes to infinity e to the x over 2x, which is still infinity over infinity, but that's all right. We'll just use L'Hopital's again. So this is the limit as x goes to infinity of e to the x over 2, which equals infinity. So this limit as x goes to infinity of f of x equals infinity. So that means the limit as n goes to infinity of a n equals infinity. And so this limit is non-zero. So the series en over n squared diverges. By test for divergence, we're adding up like infinity and infinite number of times at the very end, and so that's why it diverges. So out of these 5, there was only 1 that converged. Okay. What do you guys have any suggestions or recommendations or requests rather? What else do you guys want to see covered? Next 4 minutes. I got some fun ones. Some ones that make you say, interesting. So, yeah, I guess I'll start then with, or finish with, I will finish with Gabriel's horn. So we consider R to be the region, the set of all xy in R2, so that x is greater than or equal to 1, and y is greater than or equal to 0, and less than or equal to 1 over x. So R looks like this region. And then what we want to show that volume of R rotated about x-axis is finite, and surface area about the x-axis is infinite. So this surface of revolution, after we revolve around the x-axis, it turns out it has finite volume but infinite surface area. So if it was like a thing of popcorn, like a container for popcorn or some sort of, you could fit a finite amount in, but if you were to try to paint it, you could never fully paint it. So so for the volume, this was from last exam. So volume, that would be pi 1 to infinity 1 over x squared, and then you can see this is just pi. So this was previous knowledge. We knew this. We covered this like maybe calculus 1 even. But so for the surface area, remember surface area on x is 2 pi 1 to infinity y ds. This is the formula. So this will be, well, let's calculate ds first. ds is the square root 1 plus dy dx squared. So dy dx is negative 1 over x squared. dy dx squared is 1 over x to the 4th. And then we just add 1 to this. Okay, and we take the square root. Okay, but I'm going to factor out a 1 over x to the fourth. So I get 1 over x squared, the square root of x to the fourth plus 1. And so y, we know y is just 1 over x. So this surface area integral turns into 2 pi, the integral from 1 to infinity, 1 over x to the third, the square root, x to the fourth plus 1 dx. And so to integrate this, does anyone have any suggestions? So integrating this, any suggestions, anyone? Okay, well, I'll go ahead and tell you. U equals x squared. So that du will be 2x dx. Well, we don't have an x. That's okay. We'll just multiply by x over x. So I'll call this 2 pi, the integral 1 to infinity, 1 over x to the fourth, the square root x to the fourth plus 1, x dx. These are equivalent because x divided by x to the fourth is 1 over x to the third. So we'll just continue. We'll use our substitution. We have a 2. There's 2. We have an x. We have dx. So this is pi, the integral. We don't have to change the bounds because they're the same. 1 over u squared. Well, this is actually square root u squared plus 1 du. And it turns out that this guy right here. Yeah. Well, I actually didn't work it, but this is trig substitution. I didn't work it because this is stuff we did last time. We covered these integrals last time. So this is trig sub. You would use u equals tangent of theta. So so that like you would have du being secant squared theta d theta. And so we have, it would be secant cube theta d theta over tangent squared theta, and we're integrating this. So I think we would have, I would convert it to all sine and cosine after this, but so basically this integral will diverge. And so after you show this, then the problem is solved. So I think we're out of time though. So thank you guys for your participation. And yeah, see you next time, hopefully.